In this lecture, I'm going to be talking about optimization problems. So we first want to give a little bit of an overview of the kinds of things that we're going to need to think about in these types of problems. These are going to be word problems like our related rate problems were. So we're always going to have to start by reading the problem carefully and trying to figure out what are the unknowns and what are the givens in the problem. Our next step is going to involve often drawing a diagram and introducing notation. We're in these optimization problems, we're going to be interested in maximizing or minimizing some kind of quantity. So we're going to want to introduce some notation to represent that quantity, whether it's an area or a volume or a perimeter or whatever it is that we're interested in. And we'll have to use variables to denote some of the other unknowns and perhaps label our diagram. When we express that quantity that we're interested in maximizing or minimizing in our problem, that is what we call our objective function, because it's the function that where our objective is to maximize or minimize the value of that function. In cases where that quantity has been expressed as a function of more than one variable, we're going to need to use some of the other given information in the problem in order to get Q to be a function of just one variable. So often we're given some additional info that is related to some kind of constraints of our situation, and we'll use that information to eliminate all but one of the variables. After we've set up our equation, Q in terms of a single variable, we'll be interested in identifying what the domain is. If we recall back to some of the kinds of things that we've looked at earlier, like our closed interval method or our first derivative test, we were interested in minimizing or maximizing our quantity over some kind of interval. So we need to identify what that interval is by looking at what the domain of our function is in the context of our problem. So after we've done that, we're going to be using some kind of calculus method to identify our absolute min or absolute max value of our quantity. So we'll either be looking at using the closed interval method if our domain is in fact a closed interval, or perhaps the first derivative test for absolute extreme values, or sometimes we'll even use the second derivative test. So we'll have to identify which is the appropriate method depending on what our interval looks like. And lastly, we'll have to answer the question that we were asked in the context of the problem. So just to remind ourselves, what are these methods that we have that we're going to be able to use to find our absolute min or absolute max values? Well, we know that if we've got a closed interval, we can use that closed interval method where we go about finding our critical numbers and then evaluating those critical numbers in our original function as well as the endpoints of the interval to identify which one is the largest value as our max and which one is the smallest value as our min. If, on the other hand, we're dealing with an open interval, we may need to use our first derivative test for absolute extreme values, which involves, again, us finding critical numbers and then looking to see whether the derivative on one side of our value is positive and the derivative on the other side of that critical value is negative. So we know if we're in that situation, we're going to have or be able to justify that the value of our quantity at that critical number is a max. And if we're in the other situation where we're switching our derivative sign from negative to positive, we'll be able to identify that value as an absolute min. So these are the techniques that we want to keep in mind. So let's take a look at our first example. So here we're interested in finding the dimensions of a rectangle with area 1,000 cubic meters whose perimeter is as small as possible. Okay, so our goal is to minimize a perimeter. So we're trying to minimize this quantity P. Now I'm dealing with a rectangle, so I want to go ahead and draw my diagram. Maybe I'm going to let the width be x and the length be y. So a formula for my perimeter would be 2x plus 2y. So these are our first couple of steps. We're drawing the diagram, we're introducing some notation. We're also given this information here, which is our constraint, that the area of this rectangle has to have a total area of 1,000 cubic meters. Given that information, we know that area has to equal xy, or that in fact 1000 has to equal x times y. So we've got this as our objective function, and this is one of our constraints, and now we want to use that constraint to get our objective function in terms of just one variable. So if we solve this for y, we've got y is equal to 1000 over x. So we have p of x is 2x plus 2 times 1000 over x. So we've got our perimeter equation that we're going to be interested in, let's see, as small as possible, interested in minimizing, as 2x plus 2000 over x. So we know that one of our next steps after we've identified our function in terms of one variable is to say what the domain is. So notice here that x represents a length, so I'm going to need x to be positive. Also, because x is in the denominator here, I can't have x be equal to 0. So our domain here involves x being greater than 0, or from 0 to infinity. So we're dealing with an open interval here, so we're not going to be able to use that closed interval method. So we'll take a look at using our first derivative test. So I'm going to need to find the derivative. So we've got p prime of x is 2. Let's see, this is 2000x to the negative 1, so we have minus 2000 over x squared. So I need to identify any critical values of that. There's nowhere where the first derivative doesn't exist here, except at 0, but we know that's not in our interval. So I just need to find where 2 is equal to 2000 over x squared. So we get 2x squared equals 2000, or x squared equals 10,000. So we'd be looking at taking the square root of that. We see that the square root of 10,000 would be the square root of, let's see, 100 times 10. So we're going to have 10 square roots of 10 is what comes out to be our x value. Now to justify that that's where we actually have a minimum, we need to create a sign chart here where our number line starts at 0, goes off to infinity, where I've got 10 root 10 here. And now I need to test for the sign of the derivative on either side of that value. So if we plug in something smaller than that, like 1, we're definitely going to get a negative value here for our first derivative. We plug in something much bigger than that, we're going to get something that's positive. So we see that we do in fact have a minimum at this particular location. So we can say that the function is minimized, or as small as possible, when we've got our width, x equal to 10 root 10 meters. Now notice we haven't totally answered the question yet because we were asked for the dimensions of the rectangle, so that's asking us for both the x and the y values. So we need to take this x value, plug it back in to our equation here where we had y in terms of x. So we can say that y must be equal to 1000 divided by this 10 root 10, which was just the square root of 10,000. So we see that y is also the square root of 10,000, or 10 root 10 meters. So those are our two dimensions that the perimeter will be minimized when x is 10 root 10 meters and y is 10 root 10 meters. So let's take a look at another example. The situation is that we have a box with an open top that is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up the sides. And our goal is to find the largest volume that such a box can have. So we want to start by drawing a picture of the situation that we have here and introducing some notation so we can try to write a formula for the volume of our box, since the volume is the quantity that we are trying to maximize in this case. So we're told that we've got this square piece of cardboard that has 3 feet in length on each side, and we want to try to cut out a little square from each of the corners, and then we would fold up the sides to make our box. So I've got these little corners that I'm going to cut out. I'm going to call those corners of length x. So what is the volume of my box going to be when I fold up the sides? Well, notice that when I fold up this corner over here, my height would be equal to x. And so the volume of a box would be equal to length times width times height. So I just need to find what the two sides length would be. Well, if I cut out corners of x and x here, and this piece has side 3, then this length would be 3 minus 2x. And the same thing would be true here. I'd have 3 minus 2x. So my volume in terms of x is going to be 3 minus 2x times 3 minus 2x times x. Okay, so now we need to talk a little bit about what the domain of this would be. So in this situation, we were able to get a single equation in terms of one variable right away using the information that we had. Of course, the constraint that we were using to get our relationship here was that we had this piece of cardboard that was 3 feet by 3 feet. So what has to be true about x? Well, x is the length or the side of this little square that we're cutting out. So x certainly has to be greater than or equal to 0, but we also need that what we have left here once we've cut out x is also greater than or equal to 0. So we also need 3 minus 2x to be greater than or equal to 0. So this is going to give us some sort of upper bound on what x can be. We can also think a little bit about what x should be just based on the nature of the problem, but by solving this we see that x would have to be less than or equal to 3/2. So this makes sense if you think about if you were to have everything that you cut out basically be the whole piece of paper. If your corners were as big as they possibly could be, you would cut from the middle of the cardboard here on one side to the middle of the cardboard on the other. So you'd have these squares that were 3/2 by 3/2. So in both cases, where you cut out nothing when x is 0, or where you cut out basically everything is the corners and nothing is left with the box, you'd have a volume of 0. So our domain here for x we could use as the closed interval here from 0 to 3/2. So note that this domain allows our volume to be 0 at the endpoints. Now a reasonable choice of volume here could also be to say that the domain was the open interval from 0 to 3/2 if you said that if you decided that you wanted to make the volume always a positive quantity. In other words, if you wanted to restrict the volume and say the volume has to be positive, it can't be 0, then you would use an open interval. But we're going to choose a closed interval here. I think this is also an appropriate choice to just say the volume has to be greater than or equal to 0. And this will give us an opportunity to see how we can use the closed interval method on this type of domain. So I'm interested now in finding the largest volume of v of x on this interval from 0 to 3/2. So by reducing it to this problem, it now looks like a sort of section 4.1 problem where we want to find the absolute max of this quantity over this interval. Okay. So we've got our v of x equals, I'm going to write this as x times 3 minus 2 of x squared, just simplifying it a little bit, and we've got this interval from 0 to 3/2, and we're trying to find the maximum value of v of x. We're trying to find the largest possible volume. Okay, so to use the closed interval method, which is what I've said we're going to use here, which is our method of finding the absolute min or absolute max on a closed interval, which is what we have to first find our critical points. So that means I need to take my derivative. So v prime of x will be equal to x times 2 times 3 minus 2x times negative 2 plus 3 minus 2x squared times 1. So this simplifies here to negative 4x times 3 minus 2x plus 3 minus 2x squared. Okay, so there's nowhere where this derivative doesn't exist, but just to remind ourselves that we have to check this, we'll say v prime of x doesn't exist nowhere. So what about where the derivative is 0? So I need to look at where negative 4x times 3 minus 2x plus 3 minus 2x squared equals 0. Best way to do this is to factor. I already see I've got a common term in both of these, so I can factor out 3 minus 2x. So that would be this times negative 4x, and then times 3 minus 2x. So we have 3 minus 2x times negative 6x plus 3 equals 0. So we either have 3 minus 2x is 0 or negative 6x plus 3 is 0. So over here we would get x is 3 halves. Here we would get x is 1 half. Okay, so well, x equals 3 halves is where our volume is 0. So let's see, we're finding one of the critical points is in fact also one of our endpoints. So to use our closed interval method, we need to plug in the endpoints as well as our critical points into our volume function. So we've got our endpoints of 0 and 3 halves, and we've got our critical point here of 1 half. So if we plug in 0 into v, we get a volume of 0. We plug 3 halves in, we get a volume of 0. So it certainly seems like our volume should be the biggest at 1 half, but we need to actually figure out what the maximum volume is, because that's the question that we were asked. So I need to plug 1 half into v, so we have to do v of a half. So this is going to be 1 half times 3 minus 2 times a half. Well, 2 times a half will just be 1, so I've got 3 minus 1 squared. So this will be 2 squared is 4, divided by 2 is going to be 2. So we see that our max volume here is 2 cubic feet, because our units for this problem were in terms of feet. So this would be our final answer to the question, and we were able to justify that the maximum occurs at 2 using this closed interval method, since 2 is certainly bigger than 0. Clearly the absolute maximum is occurring when x is a half, and that gives us a maximum volume of 2 cubic feet. Okay, so let's look at another example. So let's say that we want to find the point on the curve y equals the square root of x that is closest to the point 3, 0. So when we talk about wanting to find some location where a curve here, or sometimes we'll have other situations where we're talking about minimizing a distance, that's what we have to recognize is going on here. Being closest to the point has to do with minimizing a distance. So we're going to need a formula for the distance between a point on this curve and this point 3, 0. So we need to draw a little picture. So we've got our function y equals the square root of x, and we have this point 3, 0. Okay, so I need to talk about the distance here between a point on the curve and this point 3, 0. So remember, a point on the curve would have coordinates x comma root x, and notice that this distance here between these 2 points would actually be the hypotenuse of a right triangle. So if we can talk about the sides of, the length and the height of my triangle, then my distance will be the square root of this side squared plus this side squared. So let's see, that this distance here would be 3 minus x, and this distance here would be the square root of x minus 0. Okay, so my distance, and let's see, we'll just call our distance c. C is therefore going to be the square root of 3 minus x squared plus the square root of x squared. So we have c is the square root of 3 minus x squared plus x. Okay, and we're interested in minimizing this distance. So over what domain do we need to be minimizing our distance? Well, we need to consider the domain of our function y equals root x. So the domain here would be x greater than or equal to 0, so we're looking at minimizing this over the interval from 0 to infinity. Okay, so this is not a closed interval, so we are going to use the procedure that we used in class, where we need to use our first derivative test for finding absolute extreme values. So I'm going to need to take the derivative of this function here, which is just c of x. So I'm going to have c prime of x is 1 half 3 minus x squared plus x to the negative 1 half, using the chain rule here. So I've got the derivative of my inside function, so this is 2 times 3 minus x plus 1, and this first one should also be times a negative 1. Okay, so this simplifies here to, let's see, this is going to be negative 6 plus 1 will be negative 5, and then I'll have a positive 2x, so I'm going to have 2x minus 5 all over 2 times this square root of 3 minus x squared plus x. Okay, so I need to consider where this is equal to 0 or where it would not exist. So it turns out that what's under this square root is something that's always positive, so that's always going to be defined, and there isn't going to be anywhere that would make it equal to 0. So we just need to see where c prime of x is equal to 0. So that's going to be where 2x minus 5 is 0, or where x is equal to 5/2. So we need to go ahead and make a sign chart here, and our sign chart is going to start at 0 because that's where our domain starts. It goes all the way to infinity, so we just indicate that with an arrow. So we've got 5/2 on here, so now I want to see what the sign is on either side of this point. So if I plug in something less than 5/2 like 1, I'd have 2 minus 5 as negative divided by something that's positive, so I'd have a negative here. And if I plug in something bigger than 5/2 like 3, I'm going to get something positive. So I see I'm going to be decreasing and then increasing, so I do have a min at this point. So we have a absolute min at x equals 5/2 by this first derivative test. And to answer the question, the point that would be closest is the point 5/2 comma the square root of 5/2. And so that would be our final answer to this question. Okay. So notice that depending on what kind of domain we have, that affects what kind of procedure we'll use to find our absolute min or absolute max.